let's say we have 2 points, and let's abstract for now what exactly we mean by 2 points and where they live. Just 2 points like this, and we'll name them A and B. And so the question I'm going to ask you is, what is the distance between A and B? Well, okay, that doesn't seem like a hard question, right? I can just give them coordinates, an x and y coordinate for both of them. And then using Pythagoras' theorem, you could just say it's xb minus xa squared plus yb minus ya squared, right? I mean, that's what makes the most sense. That's what you do in real world. If you want a bird's flight distance of a point to another point on Earth, well, at a close enough distance so that you don't have to take into account any type of curvature or whatever, then you just take some kind of flat coordinate and you just take that square root distance. So why am I asking this question? Well, I want to talk about briefly metric spaces and the idea of generalizing distance to just any kind of set, really. And we'll see what exactly a distance needs to fulfill as properties. So basically, a metric is a function on 2 points, and by points I just mean elements of a set, and any set really, and I'll really make that clear afterwards. So right now, to visualize them, we're basically going to just kind of imagine them as members of R squared, so just the Cartesian plane. So the points are easier to see, and you can always imagine them having coordinates if it's a little hard for you to visualize the stuff we're doing. Because the most canonical metric space is the Euclidean space of n dimensions. So a metric has to satisfy 3 properties, and the first property is that the metric evaluated on the same point has to be 0, and that makes sense, right? Because in the real world, well, the distance from a point to itself is 0, right? And the second it's sort of part of the same property, but it just says that the distance between a point and another point is always going to be greater than 0. And you could say greater or equal to 0, where the equality is when b is equal to a, as we have here. And that makes sense as well. What does negative distance mean, right? And then the second thing is that the metric has to be symmetric, which makes sense. I mean, if distance from one point to another, well, from A to B is the same as the distance from B to A. So if I walk from A to B, or I walk from B to A, well, the distance I've walked is the same, as long as I follow the exact same path, right? And to be fair, you might want to think about why that may be reasonable or why that may not. So always try to critique these things, even if they seem very intuitive. And finally, the triangle inequality. It states that the sum of 2 distances, right, is greater or equal than the sum of the final distance. So what I mean by that, if I go from one point, so let's say from, let me just get a pen, from A to B, right, that's one distance, and then I go from B to C, well, the sum of these 2 distances has to be bigger or equal to this distance, so it goes straight through. And so what that means in general is that the straight line distance, sort of, so just the straight distance from any point to the other, is always going to be the shortest distance. You can't do shorter than that, right? Because any other type of path I'm going to take, I can always, like abbreviate that as going through a bunch of points, and then using the triangle inequality, I'll always see that the sum of these distances, which is the final distance, right, is going to be greater or equal than that straight line sum. So it basically just tells us bird flight is the shortest. So that's also quite an intuitive notion. So a metric comes with a set, and I'll write the set omega. And what we get is a metric space. So the tuple of the set with this metric on the set is called a metric space. And I really mean any set, right? So I could have this like nonsense set where I just have, okay, a green square, a blue hashtag, and a red aleph. And, I mean, they don't really mean anything, they're just symbols. And we'll just say for now the metric satisfies 1 and 2, because, I mean, honestly, you just have to kind of say it, and it would be annoying to just write it symbolically for every one of the evaluations. So we'll just say that it is symmetric and that it does satisfy the identity. And then for a triangle inequality, we can just, set a few distances. So the distance between these two will put us 3. The distance between these two will put us root 2. And the distance between these two will put us 3.21. Okay? And you'll note that it satisfies the triangle inequality. So if I add 3 plus root 2, if you know root 2, well, it's at least bigger than 1, root 2. So, I mean, 3 plus some number bigger than 1, that's definitely bigger than 3.21. So it satisfies the triangle inequality for those, and you can check for the other ones as well, right? I mean, anyways, we have only 3 numbers. If it satisfies it for already, this distance is going to satisfy it for the rest as well. But you can try, for example, doing from aleph to the hashtag, and you'll see that it's bigger than just going straight from aleph to the hashtag. So just try it like that, and you'll see that it satisfies the triangle inequality. But obviously, I mean, that's not a particularly useful metric space. This is only really as far as you can really study it, defining it, and there's nothing really interesting about it. So let's look at the most famous metric space, which is the Euclidean metric space, or just Euclidean space. So it's a Euclidean set of dimension n, so it's the real numbers, set product of real numbers n times, and I've discussed the set product in my number theory videos. And so an element of Rn is, I'll write it as this bold X, and the reason I'm going to use this bold X will come clearer later because it's nice to think of Rn as a vector space. And I'll look over vector spaces in another video in more detail, but we'll briefly mention them here. And so anyways, you can just think of them as just, a tuple of numbers for now. That's all we'll care about. And so the metric from evaluated from X to Y is it's the general thing we know. It's like we had Pythagoras' theorem earlier, but it's extended. So basically, we just subtract coordinates that are at the same index, right? So if I have y1, y2, y3, all the way to yn, I do y1 minus y2 and I square it, then I add y1 minus x1, then y2 minus x2, square it, y3 minus x3, square it, and so on, and I keep adding them till yn minus xn and square it, and then I take the square root of that whole sum. So that's what this symbolic here means. And note that I could just, I could switch these two around, right? It could be instead xk minus yk. It doesn't matter because the square gets rid of any negatives that we add to it. So it doesn't really matter. And so to abbreviate it, and instead of writing d, we're going to write this sort of absolute value here, and that's sort of a canonical thing you use. And we'll see what that notation is kind of important actually later on. So let's just prove a triangle inequality. So it's clear that it satisfies the first two identities, right? The symmetric and the fact that it's 0 when it's at the same points, and you can check those. But we're gonna prove a triangle inequality that's a little bit harder. To do it, we're gonna use a piece of notation that'll just make everything easier, and we'll call it the dot product of x with y. And no, I mean you've seen dot product with vectors, so it makes even more sense why we like to think of it as a vector space. And that's just the sum of the product of our coordinates. Okay. And you can check this whole big identity here if you want. I'm not going to do that. And we're going to use another result after that I'm also not going to check. But basically, we're just saying that so this absolute value here is still the metric, right? So you can think of it as the metric distance between x and minus y, so it'd be x minus y, or y and minus x if you prefer. And if you square that distance, it's the same as, adding the 2 points. And I haven't really defined addition for 2 points, which is why, again, it's better to think of this as a vector space, because in a vector space, addition of the 2 points here, I'm really just saying add up coordinates, because we're in the normal Euclidean vector space. So I'm adding all the coordinates of each point and making a new point out of it. And so you can prove this first identity here, that the square of the metric distance between x and minus y is this dot product here. And then you can prove that this dot product is equal to this expansion of dot products, which is the law, of course, like the binomial expansion for just a square binomial. And so what that means is if I look at x minus y plus y minus z, and you'll note that that's actually just x minus z, right? Because the y's cancel. So if I look at that squared, by the first identity, we get this, right? And then expanding with this plus here in the middle, we get x minus y dot x minus y plus 2 times x minus y dot y minus z plus y minus z dot y minus z. And you'll note that this here, by the first identity, is going to be x minus y squared, and this here is going to be y minus z squared, right? And then we're going to use another result where basically these two dot products here are going to be smaller or equal to the metric from x to y times the metric from y to z. This is called Schwarz's inequality. Well, it's a little more general and normally, and because it works on norms, and I'll talk about norms in a second. But so again, we're not going to use this result, but we're going to use the result, and I'm not going to explain why it's true or anything. You can try the proof for yourself. None of the proofs I've set up till now are particularly hard; they're just tedious. So yeah, the Schwarz inequality, you can try to prove that if you want. And so that's what we're using here to get this inequality here. So here we've got an inequality, right? And here we've got an inequality. But this here is an inequality. Okay. And so then when you take this whole thing, you note that this is basically just a binomial, right? Because now I actually have just a real value. Real values being multiplied with each other. These are just symbolic numbers for real values. Because remember, these orange lines really just mean the metric, which is just some function evaluated in it. And it gives out a real value. So yeah, I should have said that earlier, but the metric assigns to the points a real value. You can't just assign whatever. And so we end up getting just this binomial expansion here of the metric evaluated from x to y plus the metric evaluated from y to z. And so what that means is that x minus z squared is equal to, well, is smaller or equal to x minus y plus y minus z squared, because remember this was x minus z. And so because we've already said that the metric is always going to be positive, well, the number under the square root is positive in both cases, so we can just take a square root and not really bother about any sign changes or anything. And so we end up getting that x minus z is smaller or equal to x minus y plus y minus z, well, with these metrics evaluated here. And so that's what we wanted for the triangle inequality. So that completes the proof, having used a bunch of results which we didn't prove, but whatever. So now, the taxicab Manhattan metric, which may not seem all that useful at first, but is useful in some cases. So once again, we're using the Euclidean space, but we've got a different metric now. Well, it still looks like D, but we're going to define it differently. So the points in Rn are still the same. And so now, instead of squaring these things and then taking a square root, we're just going to take the difference of the coordinates, right? And we're going to denote that as these double bars of a little 1 at the bottom. And this notation will become clearer afterwards, once again. So the way to interpret that is if I've got my 2 points, and I want this straight line distance, well, that's the same as just adding this distance here, which is just the coordinates subtracted by each other, and this distance here, which is just the y coordinates subtracted by each other. And so the reason it's called a taxicab metric or Manhattan metric is because, you know, if you've ever seen a map of Manhattan, it's very, well, it's a grid-like city, you know, a bunch of grids like that. And so the taxicabs in Manhattan, if they want to go from here to here, you know, they can't really afford to go in a straight line because you've got a bunch of buildings in the middle, so they have to go in orthogonal lines like this. And it can be interesting to consider this type of metric. And in general, these sort of metrics that aren't Euclidean, the Euclidean metric we use in real life, well, in real life as in like in day-to-day life, all the other metrics are still used though in a lot of applications. Graph theory, for example, and group theory both make use of metric spaces quite a lot. And actually, so does functional analysis. And I'll talk about this right now. So let's say you have some kind of natural 0 points, and a natural 0 point really is only really natural in vector space. Once again, I'll talk about vector spaces later. And so basically we say that the distance between x and 0 is the norm of x, and we write that as these double bars x like this. Okay? And so one famous norm is called the p-norm. And so the p-norm is just the sum of all the coordinates of x, and once again, x has coordinates because we're in some vector space. So yeah, that's the main difference between norms and metric spaces. Metric spaces, well, metrics are defined on sets. Norms are defined on vector spaces. Once again, I'll have another video on vector spaces. We're not going to talk more about them in here. But the p-norm is evaluated on a vector in a vector space. And so this vector has coordinates, and so basically we just sum over those coordinates to the pth power, well, the magnitude of those coordinates to the pth power, and then we take the 1 over pth power of the whole sum. And so you'll see really that the Euclidean norm, right, if you consider the Euclidean space as a vector space, is really just the 2 norm. So it'll be like this, 2, where I'll just sum over these coordinates and then I'll take the square root. And norms in a vector space, they induce what's called a canonical metric for that vector space. And the canonical metric is basically just defined as, well, d of xy. That's just going to be equal to the norm from x, well, of x minus y, like this. So that's why we all had x minus y before, because actually we were dealing with vector spaces, so we always had some kind of canonical norm. So the 2 norm is the Euclidean norm, and the 1 norm is what comes together with our taxicab metric. And so the p-norm is really, really important because if you go through and then you realize that you kind of have to extend the idea of a p-norm when p is between 1 and 0, because as it turns out, you kind of have to, the way we want to extend this is for sequences and functions, because basically right now we're just dealing with coordinates in a vector space, right? And basically if you extend the p-norm to, instead of dealing with these finite coordinate vectors, you sort of deal with an infinite dimension. So for example, you can deal with a countably infinite dimension with a sequence. And so you can think of each element of the sequence is 1 coordinate, right? And you're just summing over all these elements of the sequence. Well, you have an infinite sum, and so the sum might converge or diverge. And that's where you have to get some conditions on P for convergence or divergence. And you get different types of spaces, small LP spaces, depending on how your sequences converge. And so basically, sequences that just converge, right? They will form a small L1 space, and then you've got square convergence and so on to make different types of small L spaces. And then you've got an extra extension of that to big LP spaces, which are functional spaces. So they're spaces on functions instead of points. And this may all seem very abstract, but functions they can be evaluated on a uncountably infinite set instead of countably infinite sets like sequences. So that's why you have a big LP. And so LP spaces are very incredibly important in functional analysis. And the natural way to think about it, instead of using sums here, we'll be using integration, because that's sort of way to think about a sum over an uncountably infinite set. It's more rigorous than that. You have to deal with measure spaces and all that stuff. And measure theory does get a lot more complicated than what we're doing here. But it does give for a lot of very interesting stuff. The Holder's inequality we used earlier is actually a lot more, earlier in every video, is actually a more general on LP spaces, for example. And so, LP spaces are a great tool of functional analysis, and they sort of give you a way to think about the distance between functions. So you see some sort of extension of metric spaces here. And so now in metric spaces, you have a very useful notion of convergence. So if we have, the sequence here, un, right? Well, we can say, well, you've already seen this graph, by the way, if you've looked at my power series video. But, you take these points, getting really arbitrarily close to points, and you say that the limit to that point is p, if the point is p, right? As n approaches infinity. And that's if and only if, for all epsilon bigger than 0, there exists a big N bigger than 0, such that small n bigger than big N implies that the metric distance between un and p is smaller than epsilon. So again, this is a little hard to parse. You'll note in the video I had on metrics on power series, you had un minus p like this, right? And that's because I was particularly dealing with just Euclidean numbers. In general, you'll deal, well, here I'm doing it for any metric space. Metric spaces can just give us this notion of convergence. And convergence can be extended a lot farther than metric spaces, but right now we're dealing with metric spaces. And so these epsilons here are just representing the radii of these circles. And basically we're saying that for any small enough circle, there's always a big enough n so that all the elements of a sequence that are, farther than that index are going to be inside that circle. And those circles are all centered at p, right? So it just means that no matter how small your circle, well, you'll still have infinitely many elements of your sequence that are inside that circle and tending towards p. And so another way to write this is actually using the notion of neighborhoods. So we call them open ball neighborhoods in metric spaces. And neighborhoods, again, much more general, and we'll talk about them when we look at topological spaces. But an open ball neighborhood is just basically all the points that satisfy this equality here. And so we're just saying if un is in the neighborhood of p, it just means that the metric distance between un and p is smaller than epsilon. And so these neighborhoods are basically are exactly these circles here. So all the points inside these circles, right, they form a neighborhood of p. And that neighborhood has radius epsilon. Okay. So the idea of neighborhoods allows us to qualify a lot of different types of sets in metric spaces. Once again, this is sort of a derivation out of topological spaces. It's a lot more specific. And so one such thing, for example, is a limit points of a set. So let's say we have just some set right in a metric space, and we say that a limit point p is a point such that all the neighborhoods of p, well, and you'll note that I've noted these dotted lines because they're open neighborhoods, and once again, we're going to talk about exactly what an open set is in a second. And so all these open neighborhoods will always contain a point q that's inside the set. That's not the point p itself. So that's what's a limit point. So basically, it just means that there's a sort of infinite sequence of points inside our set that converges towards this point p. That's what it means if it's a limit point. So every neighborhood of it contains some point that's inside e. And so that's similar to our convergence property from before. Another different sort of contrary concept is the concept of an isolated point. And an isolated point just says that there exists some neighborhood of p such that no point in the neighborhood belongs to e, right? And you'll see here that the neighborhood, well, it doesn't have any point that belongs to e. So we say that p here is an isolated point. And p itself does belong to e, right? But it's just, it's not like close to any other point of e. It's just on its own. And finally, we have the notion of an interior point. An interior point just says there exists an open neighborhood of P such that the whole neighborhood is contained within this set here. And so then we have two important notions of set: closed sets and open set. A closed set is a set which contains all its limit points, right? So, and an open set is a set where all its points are interior points. Okay, and so closed sets are noted with these hard lines, and closed and open sets with these dotted lines. And so let's think about it, right? If all the points of an open set are interior points, well, take a point on this border here, right? Let's pretend this has some kind of border. Then if you take a point on the border, well, you'll note that no matter how small I make the neighborhood, there's always this right-hand side of a neighborhood that's outside of a set, while the left-hand side is inside. So we never end up actually having a set which makes it an interior point. That tells us that, in some sense, open sets can't have a border, because all points on that border would be outside the open set. And so, in some sense, the border of an open set is just a bunch of like limit points of what we have inside, right? I mean, you can get arbitrarily close to that border, but you never quite reach it. It's the same as open intervals. And in contrast, closed sets are going to include their limit points, and that tends to mean the border. And of course, it's not always only the border, but closed sets are always going to include their limit points. And so yeah, that can include the border here. Because you'll note that for a border is always, no matter how small the neighborhood, you're always going to have this one side which is inside the set. And so it makes it a limit point of it. And you have to note that closed sets and open set aren't mutually exclusive. On metric spaces, it's a little more subtle, but in general, in topological spaces and stuff, you can have things called clopen sets. And so they're sets that are both closed and open. So it's a bit of a confusing kind of nomenclature, but a closed set doesn't mean not open. Okay, and you can also have sets that are neither open nor closed. For example, in Rn, right, you can just take the half open interval. So an interval which on one side is closed and on the other side is open, that's neither an open set nor a closed set. Okay, and so there's a few properties of open and closed sets. In particular, if you take this open set here, well, let's say, this was my metric space. It's represented by this sort of plane here. Well, the set which is complement to it, so all the points that are outside this set, is going to be closed. And contrarily, if I'd considered a closed set instead, then all the points outside it, once again in this metric space, they would form an open set. And that's a general rule, that closed sets are always complements of open sets. So that's kind of fun, when you have clopen sets, for example. Well, the complement of a clopen set is also going to be clopen, because the clopen set is closed, which means its complement will be open, but it's also open, which means its complement will be closed. And a set which is neither open nor closed, well, you can't really, well, its complements can't be open nor closed either, because if it's open, then originally we have to start with a closed set, and if it's closed, then originally you have to start with an open set. That's kind of interesting characterization. And also another important thing to note is that neighborhoods are always open, and you can sort of prove that, and it comes from the fact that we were defining them with a metric, right? Well, we had un and p. You have a metric being smaller than epsilon instead of smaller or equal. But having smaller or equal, we could have closed sets. But the fact that it's smaller sort of means that it doesn't have a border, kind of what we were talking about before. And you can more rigorously prove that they're all open. So I hope that was interesting for you. It's probably not something you've seen before, except of course if you have. And it's going to be more of this kind of stuff we're going to be seeing when we talk about topological spaces someday. Not in the very near future, I don't expect, but someday we're going to talk about topological spaces, and all this stuff comes again, but in a much wider generality, and it's very interesting stuff. So yeah, see you then if this kind of stuff interests you.